Hello everyone, I'm Li Jiaqi from the Department of FinTech. Here I'm gonna present a paper from called Machine Unlearning. First of all, what is machine unlearning? Usually we heard a lot about machine learning as it helps us solve statistic problems appear in many research areas with its automation and efficiency. However, any models we get from training may subsequently mean that the data used from training have been memorized directly or indirectly be embedded into the model. So it would expose the private data to a successful privacy attack. Recently introduced legislation such as the General Data Protection Regulations in European, the California Consumer Privacy Act in the United States, and privacy legislation in Canada include provisions that require the so-called right to be forgotten. And this requirement, although controversial, mandates that companies take reasonable steps to achieve the erasure of personal data concerning, because machine learning models potentially memorize training data, and it is important to unlearn what they have learned from the data that is to be deleted. That's what called machine unlearning. It guarantees that training on a point and unlearning it afterwards will produce the same distributions of model that's not trained on a point at all. On the other hand, machine unlearning is in some extent share the same target with differential privacy, but distinct from it. While differentially private guarantees a bound on how much individual training points contribute to the model ensure that this contribution remains small, there remains a non-zero contributions from each point. If this was not the case, the model would not be able to learn at all. In contrast, forgetting in machine unlearning requires a particular training point have zero contributions to the model, which is orthogonal to the guarantee provided by differential privacy. A requirement of privacy regulations such as the GDPR or the CCP is that individuals whose data is housed by organizations have the right to request for this data to be erased. This requirement poses challenges to current machine learning technologies. The reason unlearning is challenging stems from the complex and stochastic natures of training methods used to optimize model parameters. Firstly, we have a limited understanding of how each data point impacts the model. There exists no prior work that measures the influence of a particular training point on the parameters of a model, and even though researchers have attempted to trace a particular test time predictions through the model's architectures and back to its training data, these techniques rely on influence functions which involve expensive computations of second-order derivatives of the model's training algorithm. And further, it is not obvious how to modify such influence functions so that they can map the effect of a single training point on model parameters for a complex model such as DNNs. And secondly, a great deal of randomness exists in the training methods for complicated models is the key point. For example, small batches of data are randomly sampled from the dataset, and the orderings of the batch varies between different epochs, and training is often parallel without explicit synchronizations, meaning that the inherent random orderings of the parallel threads may make the training non-deterministic. And thirdly, while training is an incremental procedure where any given updates reflect all updates that have occurred prior to it. For example, if a model is updated based on a particular training point at a particular epoch, then all subsequent models updates will depend on that training point, and therefore it is difficult to figure out the specific influence belongs to one data point. Last but not least, the learning process is stochastic as well. Intuitively, learning algorithms are designed to search for an optimal hypothesis in a vast hypothesis space. In the case of neural networks, this space contains all models that can be defined by setting the weight of a fixed neural network architecture, and therefore it is very challenging to correlate a data point with a hypothesis learned from it. So, to address the challenges in machine unlearning, the authors formalized the models of unlearning problem. The above figures illustrate the problems of forgetting. Assuming that initial state of the model is MA, and after adding a new data point called DU, the training approach can get another model called MB. And at this time, we want to forget the newly added data point DU and fall back to MA state. However, if the previous parameters are not recorded at all, that is totally impossible. So in this case, the first feasible approach is to fully rechain the MB to MC, as the green arrow shows. And one thing to be noticed here is that MC is not the original MA. And the second approach is to partially rechain MB to MC, as red arrow shows, and that is also called unlearning. The reason why machine unlearning is hard is because it should cater for 6 basic goals. First, comprehensibility. The goal of unlearning should be made easy to understand even for non-experts. And second, comparable accuracy means the unlearned model's progress decline compared to the baseline should be within a small range. And third, reduce unlearning time. The time cost of forgetting is small, and in other words, it should take less time than baseline training. And fourth, provable guarantee means after forgetting using the unlearning strategy, it should be proven that it achieves the forgetting goals. And fifth, model agnostic, which is applicable to different model forgetting strategies. And the last, limited overhead, means any forgetting strategy should not add too much burden to the machine learning process so that it is scalable to different models. Now, based on the requirements discussed earlier, the authors propose several state-of-the-art candidate for and unlearning strategies and point out the shortcomings of them. Firstly, differential privacy cannot completely eliminate the impact of the forgotten data point, and certify removable mechanism only applicable to simple models but not complex nonlinear model. Statistical query learning uses sequential training set, but the time cost is relatively large, so it is not suitable for complex models. Decremental learning looks at the problem from the perspective of data production, defines a general methods for the complete data deletion called the quintile k-means, but it has not been tested whether it is applicable to various models. Since no existing strategy can fulfill all of the goals of machine learning, this paper proposed a SISA training approach. It is short for sharded, isolated, sliced, and aggregated training, and it can be implemented with minimal modification to existing models. Simply speaking, SISA is a training mode to divide the training data into multiple disjoint shards as D1 to DS, and then train models in isolation on each shard as M1 to MS so that there is no flow of information between the constituent models. Rather than training each model on the entire shard directly, the authors divide each shard's data into slices and present slices incrementally during the training process. And in the same time, they save the state of the model parameters before introducing each new slide, which allows us to start the retraining the model from the last known parameter state rather than a random initialization. So slicing further contributes to decreasing the time to unlearn at the expense of additional storage. At inference, the authors also use different strategies to aggregate the predictions of model trained on each shot, and they find that the simplest way is the majority vote over the predicted labels. In summary, the techniques discussed in previous slides can provide a best case speed up of the multipliers of R plus 1 multiplied by S and divided by 2 in terms of the retraining time in one unlearning request. Here, splitting the model is to reduce the cost of forgetting, but it will inevitably lose accuracy. The model effect decrease with the increase of the shots, and if you want to improve the accuracy, you need to pay the cost of forgetting. So you need to find a balance between these two. However, their approach introduced several challenges. First, the approach may cause a weak learner because splitting the dataset for training will inevitably lead to a decline in model performance. And second, the approach may be costly due to the hyperparameter searching, since each constituent model needs to unify the hyperparameters, and it is important to select the initialization parameters. And as the author summarized that the SISA training approach is effective on speeding up compared to the baseline model, they try to quantify the time cost across the proposed approach with other existing approaches. However, measuring time experimentally is difficult because both hardware and software introduce variance in measurements. So to circumvent these variants, the authors measure unlearning time indirectly through the number of samples that one needs to retrain. And they show that in a control experiment, it indicates a linear relationship between the number of retraining samples and the model's training time. And these results are not only tested with the two datasets as shown, but also verified using commonly used datasets. The author discussed the expected time cost in terms of splitting and unlearning requests. For sharding, as discussed before, it is independent, and for slicing, it depends on all slides observed before them. Observe that for each unlearning request, a single constituent model is retrained when it arrives sequentially, whereas the multiple models are retrained when the requests are batched. Batch K unlearning request and retrain the entire model after every K unlearning request, and this is the same to the naive baseline of the retraining the entire dataset without the point to be unlearned. And sequential training is to train on a 1 out of x fractions of the data, and only retrain when the point to be unlearned falls into the specific dataset. The authors provide information about the dataset they use in Table 1. And for the purchase dataset, they follow a methodology similar to the Short-Curry et al.'s papers in 2007, and they curated the purchase dataset by choosing the top 600 most purchased items based on the category attributes. For ImageNet, they follow the process of Vinyard et al.'s papers in 2016 to create a dataset for supervised classification rather than the few shot classification. And here, for simplicity, the author used the same model architectures for the baseline and the proposed SISA training schemes. They consider a variety of the deep learning networks with increasingly more hidden layers as well as varying layers size. Well, to evaluate the improvements the proposed SISA approach can provide, the authors clarify 4 key issues to be addressed in the experiment. First, what is the impact of sharding on the accuracy for varying numbers of learning requests? And what is the impact of slicing? Does the SISA training improve the retraining time? And lastly, do the findings from above hold for both simple and complex learning tasks, which is related to the model agnostic requirements as discussed before. So, to understand the impact of sharding on accuracy, the authors compared the experimental accuracies of SISA training with the different number of shards and with the 2 baselines on 3 datasets. From figures, it is clear that SISA training provides high accuracy than 1 out of the S fraction baseline model, although along with less retraining time than the batch K baseline, especially when the number of learning requests is small. Observe that despite having the same benefit over the batch K and 1 out of S fraction baseline, SISA training induced more accuracy degradation for complex tasks such as ImageNet. So, from the performance of the single models trained with data slicing, the author trained each model 5 times for each number of slides on the SVHN and purchase datasets, respectively, and plot the history of the validation accuracies and confidence intervals against number of training epochs. For a small number of epochs, here the models with more slicing have lower accuracy due to the fact that they have significantly less amount of data at the beginning. As the number of epochs grows and the accuracy reaches a plateau, the accuracies of the model converges. So this result indicates that slicing does not have detrimental impact on model accuracies in comparison to the approach without slicing if the training time is the same for both approaches. In addition, slicing reduces the retraining time so long as the storage overhead for storing the model state after adding a new slide is acceptable. As more slides require less epochs to reach a same level of accuracy. Combined speedup induced by shardings and slicings in a batch setting, we can observe that as the number of shards increase, speedup increases nearly proportionally. Increasing the number of slides has diminishing returns beyond a few slides. In other words, a combination of sharding and slicing induce the desired speed up for a fixed number of learning requests. As previous findings indicate that for complex learning tasks in the real world, the common approach is to utilize a base model trained on public data and utilize transfer learning to customize it toward the task of interest. The paper replicates such a setup by performing transfer learning using a base model trained on the ImageNet to the CIFAR 100 dataset. So here the result suggests that performing transfer learning decreases the accuracy degradations induced by SISA training, especially on the complex tasks. So after providing a full understanding of the regimes of SISA, the author relaxed their assumptions and discussed how additional knowledge of the distributions of learning requests can be beneficial to the service provider. They put forward a realistic scenario that if we know that the population will follow such a distributions of learning requests, we can adapt the sharding strategy to concentrate in relatively few partitions as explained in the figure 9. and this strategy will ultimately reduce the total number of shots whose models need to be retrained. The other explore the value of distributional knowledge by distribution-aware sharding approach. As shows in algorithm 1, enforcing a uniform cumulative probability of unlearning across shards can aggregate the training points that are likely to require unlearning into fewer shards that are also smaller in size. So the distribution-aware strategy enables users to vary their probability of revoking access to the data and subsequently decrease the number of points to be retained as the figure shows. To summarize the findings, the authors discuss the weaknesses of the SISA training and provide possible solutions. As empirical evidence suggests that beyond a certain data volume such as sharding size, there is performance degradations in each constituent models when datasets are too small or if the learning task is too complex. One way to alleviate these problems is through data replication. However, one must decide which data point is to be replicated such that the accuracy of the constituent models is increased. So this selection is also a challenging problem. Moreover, even though we know that not all of the data is useful for training, a core set selection that can achieve the same performance as using the entire dataset is also difficult. And we cannot figure out the influence from the core set selection since it helps to reduce the cost of learning but also improve the cost of unlearning. Finally, the author highlights the importance of verifying the procedures of the unlearning approach in realistic application. To conclude this paper, it proposed the SISA training approach that can empower users to expect their data to be completely removed from a model in a timely manner. The key concepts related to SISA training approach are distributed training and ensemble learning, where ensemble learning approaches utilize boosting algorithms even for ensembles of neural networks to enhance its accuracy. That is the end of this presentation. Thank you for listening.